Welcome to today's HPL seminar. Thank you for joining us. It is my pleasure today to introduce our speaker, Patrick Milner, who is a master's student in biomedical engineering here at the University of Calgary, under the supervision of Dr. Brent Edwards. Patrick completed his undergraduate degree, BSc in biomechanics, also here at UCalgary, where he first became involved in research with the Nick group, working on a project that examined the effects of tensioned knee brace tights on lateral shuffle movements. Since completing his undergraduate degree, Patrick has been pursuing his master's research, which now investigates how advanced footwear technology influences foot bone loading. He is currently in the process of writing his thesis, making this the perfect time for him to share his findings with us. And actually, he just confirmed before this presentation that he defends on December 10th. So wish him luck after the presentation. Outside of his academic work, Patrick is the co-founder and head of product design at Ghost Rowing, a new high-performance rowing and endurance sport apparel brand. Well, fittingly enough, he was also a captain of the Dinos rowing team, so that's very cool.
Yeah.
Today, Patrick will be presenting his talk titled Metatarsal Loading in Advanced Footwear Technology. Thank you, Patrick.
Thank you for the introduction. Like Ashna mentioned, today I'll be presenting on metatarsal loading in advanced footwear technology. When we look at the kinds of shoes athletes are wearing, they've really evolved in recent years, mainly with the introduction of what has now been coined as an AFT, or an advanced footwear technology. These shoes have dominated the world stage at elite level races like the Olympics, Boston Marathons, or World Championships. However, when we also look at recreational runners, we see a growing prevalence of your everyday runner using these shoes not only to race, but also for their everyday training. If we look at some of the statistics behind this, when a group of amateur runners were interviewed, over 67% of them wore AFT shoes at least once a week as part of their training rotation. If we look at the higher frequencies of use, 27% wore them at least, up to 3 times a week, and 5% wore them for every single day of running. There are a few key characteristics that make up an AFT shoe. Notably, a highly resilient midsole foam. This is usually a PEBA foam or a TPEE, depending on what shoe manufacturer is making the AFT. There's also a large toe spring, which is defined as the curvature between the pivot point or pivot axis of the shoe and the toe of the shoe. In addition, these AFTs also have a composite element inside them, so either a carbon fiber or a fiberglass plate running throughout the midsole, increasing the longitudinal stiffness of these AFTs when compared to conventional running shoes. There are also a few key biomechanical changes that we observe when individuals run in AFTs. Notably, due to the increase in longitudinal stiffness, there is a significant reduction in the peak MTP, or metatarsal phalangeal joint flexion angle, in carbon fiber or AFT shoe conditions. Notably, there are also reductions in observed forefoot pressures under kind of that metatarsal region, as well as increases to stride length. Overall, AFT shoes are changing the way people are running, even if it is to slighter degrees. This starts to bring up this question as to whether or not these biomechanical changes are predisposing individuals to injury. So we know that people run slightly differently in AFT shoes. However, we don't have much information as to if these changes are leading to increases in injury risk, which is one of the questions we wanted to answer. If we look at the public sphere and social media posts, journal articles, magazine articles, there's this growing dialogue asking this question are carbon-plated running shoes, are AFTs leading to injury? Are people paying a price for improved performance with injury risk? If we look at the root of a lot of these social media posts or magazine articles, they almost always reference this one article that was published in 2023 that made the observation in a very small subset of runners. This was an N=5 case study that made the claim that maybe AFT shoes are increasing the risk of bone stress fractures in the foot. However, if we dissect these 5 case studies, almost all of them, 4 out of the 5, had a predisposition to stress fractures. So they either had a stress fracture before or some type of bone abnormality. And in 3 of these runners, it was their first time ever wearing this footwear. So they had no prior experience to running in AFTs. And this starts to poke some holes in this potential dialogue and starts to raise this question of, are these shoes actually leading to injury risk, or are we just looking at cases where people happen to get injured in AFTs? We really have a very limited understanding of the actual mechanical loading environment within the foot when people are running in carbon fiber or AFT shoes. And this is what we want to try and dissect and answer as part of my research. For my work, I looked specifically at the metatarsals, and this is due to 2 key reasons. Firstly, AFT shoes significantly alter the biomechanics of the MTP joint. Like I mentioned previously, AFT shoes, when individuals run in them, there's an observed reduction in the MTP flexion angle, so that joint is bending much less. Additionally, the metatarsals are one of the more likely bones to experience a stress fracture, with over 20% of all running related stress fractures happening in the metatarsals. This is most common in the longer metatarsals, such as metatarsals 2 and metatarsals 3. When it comes to actually predicting stress type injuries, this is dependent on 2 things: on stress magnitude, so how much stress is the bone subject to, and the number of loading cycles that the bone is subject to before it's allowed time to recover and remodel. For our study, we wanted to answer the question of how are AFT shoes influencing metatarsal stress, to again, just try and give us some context as to what this might mean for injury risk. Our prediction was that AFT shoes would be reducing peak stress. This was in part due to some previous literature that showed reductions in this forefoot pressure under the metatarsal region. To answer this question, we did 2 studies. Our first study had 10 male recreational runners, in which we did overground running trials, and this was an acute intervention. So they ran for a very short period in each shoe condition. For study 2, we looked at 10 female recreational runners, in which we ran them for an hour long in each shoe condition while on the treadmill. For our 2 shoes in this study, we chose the Nike React as our control shoe condition and the Nike Vaporfly as our AFT shoe condition. We chose the Vaporfly because it's relatively common in literature, with a handful of other papers using this shoe already. And it's also very commonly known in the running world as one of the more prominent AFTs. When we looked to choose our control shoe, one of the things that we wanted to have significantly or measurably different was this longitudinal stiffness. So we measured the bending stiffness of these 2 shoes and found that the Nike React had a longitudinal stiffness of only 4 newtons per millimeter versus 18 newtons per millimeter in the Vaporfly, suggesting that confirming that the Nike React indeed did meet this criteria of having reduced bending stiffness. For this study as well, we did not control for mass, and instead had individuals wear both shoe conditions like they would if they were using these for their training or their racing, to create a real world loading environment. For study 1, a little bit of a deeper dive into our protocol for this one. Like I mentioned, we had 10 male recreational runners, all of which were shoe size 10. We had our 2 shoe conditions, the React as our control, and our Vaporfly as our AFT shoe. We ran these participants for 7 repeated overground running trials at a fixed speed of 4 meters per second. During these trials, we captured plantar pressure through the use of sensor insoles, motion capture with an 8-camera Vicon system, as well as a subset of our participants receiving weight-bearing CTs to capture subject-specific geometry for the bones of the feet. For analyzing and interpreting our pressure data, we started with the extensor insole and broke it up into distinct regions for each metatarsal, as well as corresponding toe regions. And this is what we used to map our forces onto our model when we do get to that. Looking very briefly at our pressure data, we have the AFT shoe in red and the control shoe in blue, and we notice a significant reduction in pressure under these metatarsal regions when running in the AFT shoe. Now, how are we moving from pressure data into actual measurements of force and stress? To do this, we started with a musculoskeletal model. So we had a 2-segment model with the metatarsal and the toe as 2 distinct segments. From here, we rigidly constrained the metatarsal in 3 dimensions and did a quasi-static analysis to determine the forces acting on the metatarsal head. Starting off with our toe forces, we mapped the toe forces from the extensor insole onto the toe segment and used the plantar musculature to resolve the moments about the MTP joint, using some predetermined measurements from cadaveric studies to determine the position and the vector at which these were acting at. From here, we got our joint reaction force. So the reaction force of the toe acting onto the head of the metatarsal. We could then add in our metatarsal force, which we measured from the extensor insoles onto the metatarsal. And in conjunction with the dynamic metatarsal angle that we calculated from our motion capture, we were able to convert these into an axial and shear force component. So the axial force component acting directly through the metatarsal and the shear force component acting perpendicular to that at the head of the metatarsal. These 2 forces were then used as inputs or boundary conditions for a finite element model. For this model, we distributed these axial and perpendicular forces across the metatarsal head and rigidly constrained the base in 3 dimensions to estimate the stresses that the metatarsal experienced while running. For creating our meshes, we started with subject-specific weight-bearing CTs, in which we would mask out the metatarsals and convert them into a tetrahedral mesh for analysis. And this was all performed in Mimics and 3-Matic. For our material properties of our finite element model, due to some limitations of the cone beam CT scanner, we used uniform material properties for the entire metatarsals. So we assigned a Poisson's ratio of 0.3 and a Young's modulus of 20 gigapascals for every element within our mesh. When we start to look at some of our data, this is our axial force component between the control shoe and the AFT. We saw a significant reduction in this axial force component for metatarsal 1 and 2. However, when we start to look at our shear force or our perpendicular force component, we observe no statistically significant changes between our 2 shoe conditions. Furthermore, looking at a subset of our participants for this first study, we had an N=4 in which we looked at stress measurements, and the overall trend for metatarsals 1 and 2 were that we observed a decrease in this stress component. And most notably, none of these trended toward increases. In summary, for this first study here, we observed a reduction in the peak pressures acting under the metatarsal region, a significant decrease to axial force, as well as trends toward a decrease in metatarsal stress. Overall, these results of this first study demonstrated that AFT shoes were not increasing the magnitude of stress in these first and second metatarsals. However, this study did come with a couple limitations that we hope to answer with our study 2. This first study did not look at whether this relationship is the same between men and women, as well as this was a very acute observation, looking only at a short time sample of overground running. We tried to answer these limitations with our second study, in which we had 10 female recreational runners, this time with shoe size women's 7.5 and 9, running in the same 2 shoe conditions. So the React as our control and the Vaporfly as our AFT. For this study, we ran individuals for 45 minutes at 65% of their VO2 max, followed by 15 minutes at a slightly elevated pace, which equated to roughly 75% of their VO2 max. It was during this last 15 minutes that we sampled our musculoskeletal data. For our measurement, we had the same exact measurements in the study. We collected plantar pressure and motion capture for all of our participants, with the addition of subject-specific weight-bearing CTs for our entire sample instead of just a subset. Now, if we're looking at some of our data again, when we start to look at this axial force component, again, we observe a significant reduction in the axial force, again, in metatarsals 2, 3, as well as metatarsal 4. Looking at our shear force component now, similarly to the first study, we observe no significant reductions or changes to this force component. And then looking at our metatarsal stress values, again, we did not see any necessarily trend or significant changes in this force component. When we did look at our data, we observed noticeable amount of variation in our results. And this led us to try looking at a subset of our participants. And for this, we looked at grouping our individual or participants by speed, looking only at subjects that were running over 3 meters per second for their trial. When we do this and start to look just at this faster subgroup, we again see the reductions in axial force. This becomes slightly more prominent in the subgroup, as well as now trends towards significance in reduction of this shear force component. So metatarsal 4 did see a significant reduction in this shear force, as well as the remainder of the metatarsals trending toward a decrease in this force component when running in the AFT shoe. Now, when we looked at metatarsal stress for this subgroup, we saw significant reductions in this stress component for metatarsals 2, 3, and 4, as well as general trends toward decreasing metatarsal stress in this subgroup. In conclusions, when we look at these 2 groups separately, when we looked at all of our runners as part of this second study, we found decreases to our axial force component. However, the shear force and the peak stress remained relatively unchanged between our 2 shoe conditions. Looking just at our high-speed subgroup, we again saw that reduction in axial force. However, we also saw decreases in the shear force component and the peak stress from our finite element model. In summary, looking at these 2 studies together, AFT shoes may be decreasing peak metatarsal stress. At the very least, they are not increasing it. Additionally, there's a potential interaction between either speed or running ability on these results, as we saw in this second study. Kind of closing everything off and tying it together, throughout both of our studies, we saw nothing to suggest that AFT shoes would be increasing metatarsal stress, and consequently, that there would be no explanation as to why these shoes would cause an increase in injury risk, at least from a mechanistic and loading perspective. Thank you very much.
With that, the floor is open for questions. Who would like to start us off? Okay, while I'm waiting for your hands to go up, I'll start with mine. So to me, when you first talked about your hypothesis and study launch, you said that you expected decreases, or you hypothesized that there would be a reduction in the peak stress
That is
or
correct.
pressure. And I'm not sure if I missed it, but was that based on studies that were showing trends in that direction? Because I would expect you to,
Yeah,
think that, okay, maybe AFTs don't increase like you have been summarizing, but to hypothesize a decrease, where was that coming from?
so that came from this one song study that was published in 2024. It was a modeling study, so they only looked at one participant, but ran a variety of computational models looking at variables like plate thickness and plate stiffness. And they found that with the inclusion of a carbon fiber plate in the midsole of a shoe, like in the Vaporfly, they saw reductions in this forefoot pressure. So building off of that, we made the hypothesis that with our musculoskeletal model, we would see decreases to the axial and shear force components solely due to this reduction in pressure.
You,
Can you maybe comment a little bit on when during the stance phase the peak pressures actually occur?
Yeah, so when we looked at the metatarsal pressures, those occur roughly around 70% of stance, so close to toe off, kind of in that push off phase of running. We did model the entire stance phase and then only sample or only ran our models at the point of highest pressure and stress. Welcome.
one more thing I was actually curious about.
Mhm.
You used the same two shoe conditions in your first and second study.
We did.
The first one was a male, population or sample size, and then the other one was females.
Correct.
Are the material properties the same for the female shoes that you buy, or are they different?
The actual materials themselves are the same, but due to things like changes in length, we would see changes to that stiffness element. So like the carbon fiber itself, I believe, is the exact same. I don't have that data like on hand, but
So when you say carbon fiber stiffness was bending stiffness the same, like the 18 Newton per?
so I believe the thickness of the plate itself is the same. So with a shorter shoe, same thickness plate, you would see a slight increase in longitudinal stiffness.
I asked because I'm wondering then, a lot of times people talk about the fact that AFT and the benefits or risks that come with AFTs might depend on subject specific characteristics like mass and how much you can bend the shoe. So interesting results in your female data set, which might indicate that a greater bending stiffness for someone might be, limiting more of that implant flexion and giving a greater reduction in those variables that you were, yeah.
Correct. And additionally, when we did start to look at speed as well, it seemed like there was some effect there, or at least grouping based on speed in our study showed different results for our high speed and our slow speed sectors.
Ariana? Great questions.
Yeah.
So my first question is, what part of the damage do you think is contributing to this decrease in heat pressure? Is it the cushioning, the plate?
So I think it's twofold. Largely, it's due to the cushioning element, so it is a highly compliant foam. However, if this shoe, this is speculation, I believe that if the shoe were made without the carbon fiber plate, it would lack the structure to actually support the foot, and you would not necessarily bottom out the foam, but you would bend it much more than you would a conventional running shoe, and that may lead to changes in force distribution or pressure under that metatarsal region.
My second question, so my understanding, you had two segments, you basically replaced the toe segment with the forces that it like enacts onto the other segments.
Correct.
How did you apply these forces?
Cause
Yeah.
my question just is, you have a, like, where it's an involved socket joint,
Mhm.
it probably distributes forces about the entire head of the metatarsal instead of just the two segments that you.
That is correct. So for a musculoskeletal model, that one was like a two-dimensional model. We only looked at like point loads acting on the head of the metatarsal. However, when it came to our finite element model, we distributed these evenly over the entire head of the metatarsal.
Do you think it would be more accurate if you have the toe in there at day and then you made like a contact point or like a contact fixture and then apply forces onto that segment?
It could be. With any model, there's always trade-offs between complexity and compute and accuracy. This is a model that has been used quite extensively previously. I think its first introduction of the musculoskeletal model was in the late 1990s, and it's still used today with iterative improvements, mainly on the finite element modeling side of things. So if we did include two segments in our finite element model, yes, accuracy might improve a little bit. However, with some other validation studies that have been done in the Edwards lab, we found this model to be quite reflective of what's measured in cadaveric studies.
So you'd say it's approximately uniform with this.
Roughly, yes.
My last question is, so the way CT can find the shape of the bones,
Correct.
can it find like anything else like density and like the shape?
So, yeah, that is one of the trade-offs of our specific weight-bearing CT scanner. So it is a cone beam machine versus a clinical machine, which takes like individual slices. This takes like an entire, well, the beam itself is a cone, and this leads to attenuation in the signal as it moves through the field. So your gray values in one position might not correspond to the same density of that same gray value in a different position. So for that reason, we only used it for geometry. So geometry is still reliable. However, due to this variance in gray values, we chose to use uniform material properties.
You've done any sensitivity tests to see if like having the gradient of densities or different densities would change your results in the order?
I haven't done that myself. When it comes to cone beam CT scanning for applying different density values, again, just based on those grayscale values, the best method seems to be using artificial neural networks to assign density values based on this kind of gray value attenuation. So for the scope of this project, we didn't feel it was a meaningful benefit. However, like with any model, the more accurate all of the inputs are, the more accurate your output is. For comparing the two shoe conditions, however, I do believe that using this material uniform properties still allows us to compare the two shoe conditions. However, if we wanted to say definitively how many steps someone would take before that bone fails, we would need to use subject-specific densities for that.
Thank you.
Yeah, you're welcome. Thank you.
Other questions from the audience?
Thanks, Patrick. I'm still learning about finite element modeling. I was just curious how you defined the thresholds for the magnitude for the one stresses.
Yeah, so our magnitude, when we measure peak stress, we took the 95% stress interval for our finite element model and said that was like our peak stress. And that's mainly to filter out any artifacts. So if there is like a very sharp point at one node in our element that shoots the stress value all the way up. So for our peak stress measurement, we can't just take the highest recorded stress in that bone. Instead, we look at an interval. So like for this one, we took our 95% stress interval to that. Like, was that the answer?
And then is it a monotonic condition for the finite element modeling, or is it like a simulation of
Yeah.
cyclical loading?
So what we did for our finite element modeling is we broke stance phase up into 10% intervals and then ran our model at each 10% stance, but we didn't feed it any history from before. So it's just measuring the deformation and the stresses subject to that specific load. So we had nothing but cycling in there. It was more just like monotonic. This is the load input that we give. What is the deformation? What is the stress measured?
Do you think the peak one of these stresses would be more distributed if you're on a cyclical loading model and simulated? Like, can you assign degradation properties to the elements?
We could assign degradation properties to the elements. I think that starts to answer a slightly different question. That would be more on like the fatigue failure side of things. So if we did want to say or estimate how far someone can run in each shoe condition, that would be the best approach to use. When we're just comparing these two shoes for the purpose of saying which one has higher stress inputs to the metatarsal, I think we would see roughly the same comparison between those two approaches. We're really just trying to figure out how much stress is the metatarsal under, and if we were to assign degradation properties to it, the model in which we feed larger force inputs to, like the control shoe condition, would see more rapid degradation, but I can't speak to the actual degree of that.
Isn't that a little bit important in your second study where you were looking at the effective time? And
Yeah,
I can't remember if you showed the results of the effective time,
Yeah.
but I do remember from our conversations, you didn't find it.
so we didn't look specifically at the effects of time in our second study. Instead, we were looking more at how individuals would respond after having run in the shoe for a prolonged period. So not necessarily how does that change over time, but allowing an individual to familiarize with the shoe and to revert into whatever their more comfortable or preferred movement pattern would be, instead of just repeated short trials. So that was our goal with that hour-long study. For kind of that degradation side, if we were to include it, I don't think our interpretation of the differences between our two shoe conditions could be different. It would just give us more insight into the actual fatigue failure risk.
So your results from your second study were at the end point of the hour-long run?
Correct, so they were measured during that last 15-minute interval, right in the middle of that.
Colin?
Patrick, did you see spatial temporal differences like you talked about in your introduction, no longer running study with females? Like, do they have increased stride length or anything like that in those?
They did, but it did vary by that speed component as well. So we did do our two subgroups at slow speed and high speed subgroup, and did our further analysis in the high speed subgroup. There was variation in there, and then when we did look at things like cadence, that did change between our two shoe conditions.
What would you speculate that would have on like, you know, you're looking at measures of metatarsal stress loading like one cycle, right?
Correct.
Thinking about this like fatigue, what do you think? Like, I don't know what you found with spatial component stuff, but what do you expect that would extrapolate out over an entire run rather than this is?
Yeah. Extrapolating that over the entire run, I think would lead to even more favorable results for the AFT shoe conditions, specifically due to increases in stride length or decreases in cadence. So you're taking less steps with slightly less stress in the metatarsals. Long term, that would mean someone in theory could run further with a lower likelihood of fatigue failure.
Do you think that load's going somewhere else? Like, can you speculate on that?
Yeah, I think, yeah, it has to be going somewhere else, whether it's absorbed or distributed into the shoe itself or higher up onto the skeleton. At this point, I don't have the information to say that, but I know there is other work in the lab that is starting to look at this and try and answer that, because that is a point of discussion. We do see changes to the foot biomechanics. We're starting to see this decrease in metatarsal stress, but for where that is going up skeleton, we really don't have an answer for that. So
One more question.
go for it.
You showed the graphics with some specific results for the shear force that they did in the second study.
Correct.
We have one participant that had a reduction. Control. So you think that's coming from like the bone orientation, or is that just a reduction in pressure, or is it a combination? What's going on there?
I think it would be a combination. So we did sample on 2 different weeks. They would come in on week 1, run one shoe condition. From the second week, run in the second shoe condition. We did ask individuals to control their running volume and everything leading into it. I think the shoe definitely did have an effect, and part of this effect is coming from the shoe, but I think it's also. We also have to take into account that that individual may have been running slightly different between these 2 days, not necessarily dependent on the shoe, so.
All good.
Very clear talk, I enjoyed that.
Thank you.
I have a couple of questions, and first, why are you interested in stress and not strain?
That's a good question. So the reason we looked at stress instead of strain for this was mainly because of those uniform material properties that we applied to the bone. So since we aren't able to get the subject specific densities and material properties for our model, we decided to look at stress instead of strain.
That's what I thought the answer would be, and then I wanted to ask. I think a lot of people would argue that stress factors occur a lot in elite female runners that are very skinny and overweight, that presumably have also altered bone qualities. And so my question is, might stress and strain really not be so important for a stress fracture rather than the bone that you're bringing into the race?
The bone is definitely a big part of the equation. I think one of the biggest parts. So if the individual does have compromised bone density or a previous injury, they are at a much higher risk of a stress fracture. For the purposes of this study, and trying to just compare these two shoe conditions, I would still say that even if an individual with compromised bone quality were to run in the EFT shoe, they would still see a relative decrease in stress compared to running in a normal shoe. But overall, for that individual, they would still be at risk of stress fracture just due to their bone composition.
And almost going back to Colin's question, but a little bit on a different level, you know, when you say you have this decreased pressure under the metatarsal, and I would assume that the reaction force is about the same. I'm not sure if that's true. Then you would have to have pressures that are greater in other places.
That is correct.
So
So
then the question becomes, you know, would these other places then be more at risk for getting injured, although you protect the metatarsal?
and that is very possible. When we do look at the pressure map under, well, for the feet of individuals running in AFT shoes, compared to conventional shoes, it is a little more distributed. We don't necessarily see those large concentrations under the heads of the metatarsals, but it starts to be distributed a little further back in the foot as well. There's a little more soft tissue in that area, which might shelter the bone. Additionally, by moving those pressures or forces back a little bit, now they're acting closer to the midpoint of the metatarsal, or at least not at its most distal point, reducing that lever arm. So specifically for the metatarsals, I see this as overall net positive. However, if we do start talking about some of the bones further back in the foot, it is possible that some of this force and pressure is being redistributed onto them, but I don't see data that would necessarily suggest that would be harmful at this point.
I don't know the pressure sensor that you're using, but when you say pressure, I assume this is perpendicular to the surface.
Correct.
And but there will also be forward and backward forces that you presumably then don't capture.
There would be.
What do you think the effect of those might be?
I think the effects for the purposes of our model would be relatively minor. Our pressure insole it does measure perpendicular to the shoe, is like what we are measuring specifically. Or looking at forces acting in other directions. I don't believe they would be of large enough magnitude to be injurious, is my speculation. However, I don't really have the data to support that or to validate that. Because you're correct that when we do look at the ground reaction forces from the force plate, they're roughly similar between these two shoe conditions. They're running at the same speed, but this force is going somewhere.
The other thing I was wondering, if I saw your rendering, your final element modeled properly. Do you consider the bones to be like isolated there, or do you account for ligamentous and muscular connections and how that might potentially affect the distribution of the loads between the metatarsals?
So we do assume that they are relatively isolated, so we don't look at any of the soft tissue connections. The closest we come to that is distributing our fixed boundary condition on the proximal end of the metatarsal over the entire surface, as well as distributing the forces over the majority of the metatarsal head. That's the closest we come to modeling the actual contacts. But in terms of soft tissue, we did not include that in our model.
And just a technical thing, when you talk about these peak stresses that we have, and the way the forces seem to be and the way the bone seems to be, it seems to me that some of these stresses will be compressive and others will be tensile.
That's correct.
So so when you show these peak stresses, are they compressive or tensile stresses?
They would be largely compressive stresses. So we do. Well, like we have this shear force component acting on the head of the metatarsal, which leads to compressive stresses on that top side of the metatarsal. And additionally, this axial force component leads to compressive forces throughout the entire metatarsal, reducing those tensile forces from the shear one on the bottom of the foot. So our peak stresses are compressive stresses.
And just staying with this slide, you talked a little bit about it. I'm fascinated that, let's say metatarsal 3, you have forces as low as maybe 120 or 30 and higher than 400. How do you get that?
Part of that,
3 times different?
yeah. Part of that is subject specific variance. Well, a big part of that is subject specific variance. And this could be things like running style, the weight of the individual. This one was controlled speeds, so everyone was running at the same speed. However, they all had different running styles, different foot contacts, and this can lead to this large variation in our force components. And it also comes into things like the actual metatarsal angle as well. So these forces are very sensitive to the angle of the metatarsal.
Yeah, and at the very end here in your conclusion, you mentioned that this depends also on the running ability. What do you mean this running ability?
So when we looked at our second study, we based their running speeds off their physical fitness. So we did a VO2 ramp test to determine what a sustainable running speed would be for them. Coincidentally, we found that in our slower runners, which were also less experienced runners, they responded differently than the higher speed and more experienced subgroup, suggesting that there's some interaction either on the speed front or on this running ability front that we weren't able to properly flesh out as part of the second study, but that might be grounds for future research to look at, are these responses different in purely recreational runners that run once or twice a week versus experienced runners that have been running for 10 plus years and run almost every single day.
And maybe a last more philosophical question, if I understand this correctly, the foot is kind of made a bit stiffer, this shoe, this is plate, and I'm a believer in evolution. So why didn't our foot develop to be stiffer? Or in other words, what is the advantage or the disadvantage of this shoe is that makes our foot a little bit stiffer?
So we do see performance advantages. There's been quite a few studies that show that when running in these AFTs, we see a significant reduction in the cost of transport. And it's possible that this is speculation, but that our evolutionary path wasn't necessarily to boost performance as much as possible, but maybe there's some secondary benefit to how our foot is currently built. So whether that be something like robustness and like the longevity of the foot, injury risk, the risk of Achilles tendon stresses. All of those things may have played a part that made our current foot design the most optimal from an evolutionary perspective, but not necessarily from a competitive runner perspective.
Interesting, you mentioned Achilles tendon. Did you by any chance try to evaluate what the stresses might be on the Achilles tendon?
That wasn't something that we looked at as part of the study. However, we did look at the plantar or the forces of the plantar musculature, and those are very much dependent on toe forces. So as toe forces go up, the plantar musculature needs to resist that moment even more.
So that would mean you would speculate then that the Achilles tendon forces go down in the.
Not necessarily. I would.
You didn't look at the center of pressure there.
No, we didn't look at center of pressure. We only looked at the pressure concentrations under those specific metatarsal regions. If I have to speculate based on other literature that I've seen where the center of pressure does seem to be moving slightly posteriorly in AFT shoes, it's feasible to say that maybe there's a reduction in Achilles stress, but again, the study didn't look at that. I think we need to have more things with ultrasound and specific modeling of the Achilles tendon to say definitively.
Great, thanks.
Any last questions for Patrick? I don't.
So you would think that evolution is the reason that the foot is so well developed, or what? How did I explain that?
I think evolution is the reason that we are built how we are to a certain extent, and the foot is part of us as a human being. It has been optimized for running in certain extents, depending on who you ask. Some people.
What has been optimized?
What has been optimized?
Yeah.
Everything from us having two legs to our musculature being where it is, having shorter toes compared to fingers for toes. All of those have iteratively changed through evolution.
The fact that the hands and the feet are similar. These are the optimization of evolution.
It depends optimizing for what. If you ask a monkey, it thinks that its hands for feet are very good. I think they would have been optimized for its environment. Our environment, depending on where you look at and what literature, we are endurance hunters primarily, which required running, and consequently humans or prehistoric humans that could run better were favored in the gene pool, and ultimately their characteristics were passed on.
It's a nice story, but I don't believe it.
Yeah.
Some people would argue that things are, evolved not necessarily for optimal performance, but for optimal adaptability. That insects and animals that seem to have survived for a very long time, longer than humans so far, seem to be the ones that are very adaptable. When things change, they can adapt quickly.
That's correct.
So maybe it's not really an optimal performance design, but how can you adapt to a changing environment in the best way?
Yeah, to be robust and resilient across a variety of landscapes, variety of tasks as well.
For example.
All right, I think with that, let's thank Patrick for his talk.